So welcome to the second half of calculus. So in one sense, well, we're 3 months in and we've only got a few weeks left. What's going on? Well, we've done a lot of the heavy lifting for this, as we'll see by the time we get into section 5.3. We will see that we've done most of the heavy lifting that we need. We just need to develop the vocabulary, we need to develop the terminology, the notation, and then we can rely on some of our skills from the first half of this course. Okay? But we're moving on. So there are really two big questions in calculus, and we've answered the first one. We've explored that in great detail. The first one sort of had two parts. How do I find the slope of a tangent line to a curve at a point? And how do I talk about instantaneous rate of change to a curve? And that's what we discussed through this first half of the course. Okay? And we answered that essentially by computing the what? Derivative. By computing the derivative of a function. Okay? So that is essentially the first half of calculus. There's differential calculus, and now we're getting into the second half. So the second question that we want to talk about, and I'll try to motivate our reasoning here towards the end of this lecture as to why we're interested in this. But the second question that we want to ask is, how do we find the area underneath a curve? And this is determined by computing what we're going to call the definite integral. Of a function. Okay? Word integral should be ringing a bell, but we're not quite sure how it's all connected just yet. Okay, so for the area problem, first of all, let me say that there will be times where I'll just ask you to pull upon your normal understanding of geometric shapes. So if it turns out that this curve has a triangle shape to it, you can just use your area for a triangle. Or if it's got a rectangular shape to it, you know how to calculate the area of a rectangle. Or if it's got a semicircle shape to it, you know how to compute the area of a semicircle. Okay? So you can use your basic geometric shapes, and sometimes you'll be saying, oh, I can't figure this one out, and then you say, oh, of course, I just used this basic shape. Okay? So let's go ahead and look at this one here. We're asked to find the area underneath the curve, and I guess I should add this here, and the x-axis. From x equals 2 to x equals 8 for this function right here. What is this function right here? F of x equals 5. What does that function look like? It's a horizontal line, right? So here it is. Here's the graph of it. Maybe something about like that. Okay. There's the graph of f of x. And we're asked to find the area underneath this curve from x equals 2 to x equals 8. So we're asked to approximate this area. Well, not to approximate it. Let me be clear. We're asked to find the exact area underneath this curve right here. Well, this is one that is just a geometric shape. Right? What's the area underneath this curve? The area underneath this curve is 30. How do we get there?
6 times 5.
So the height of this is 5, and the width of this is 6. And I want you to think of a rectangle as a base times a height. So the area of a rectangle equals a base times a height. Okay, so in this case, the base is a base. Actually, let me just, for fun, let's change that around. Let's say height times a base. Height times a base. Okay. So what was the height of this? The height of this was 5, and the base was 6. So the area is 30 square units. Okay. I think you'll be doing well in this unit if whenever you see a product of two numbers, you go ahead and think of a product of two numbers as an area. You could always create a story problem where you're calculating area based on of a rectangle based upon those two numbers. So that might be helpful for you going forward.